Okay, so last week we started talking about fundamentals related to compressible inviscid aerodynamics, and we covered some fundamentals. Last time we were talking about fundamentals related to thermodynamics. The first thing we discussed was basically first law of thermodynamics, and it's basically here. It's basically the first law of thermodynamics is the conservation of energy. So we talked about it, and when we define a system, which could be basically your fluid particle, for example, or let's say a part of the fluid that is enclosed by an invisible boundary. So that's part of the fluid, which we could define as a fluid particle, interacts with the surroundings. So how? In terms of energy interactions, that is. In terms of heat transfer, there could be some interactions. And in terms of work done through expansion or contraction of this system with its surroundings, there could be some interaction. So whether it's a heat transfer type of interaction or a work type of interaction, that affects the internal energy of the system. So it could increase, meaning E, internal energy could increase or decrease, depending on heat and work interactions that are occurring between this system and its surroundings. So we call it an adiabatic process if there is no heat interaction. So if delta Q is actually zero. We call it also, we defined it last week, we defined what a reversible process. By the way, these are all kind of a reminder for you from thermodynamics. Reversible process is that there is no dissipative phenomena that is occurring. That does not mean that heat transfer is zero, okay? There could be heat transfer in a reversible manner, that it could be happening. But what is missing is the dissipative phenomena cannot exist in a reversible process. What is a dissipative phenomena? Like friction, for example, that is occurring between two substances, between two solids, for example, friction, or between a liquid and a solid due to viscosity, or even between, or I mean, fluid and a solid, and even between a fluid and a fluid due to different friction-based mechanisms related to viscous action. So therefore, if there are these dissipative phenomena that exist, which then makes the system what we call an irreversible, or makes the process that the system goes through, makes it an irreversible process, okay? So the thing is, this energy equation as it's written here, the total energy of the system changes based on heat transfer and work interactions. That does not necessarily say, for example, let me give an example. Let's say we're talking about the process where work is zero, okay? So we only have, let's say, heat transfer interaction. So depending on the heat transfer interaction, the energy of the system could increase or decrease. So delta Q can be positive or negative. So heat transfer could be flowing one way. If you take a look at this here, I had two. I have this curve with two arrows on both sides, right? Which means that delta Q can happen both ways. So it can go in to the system or it can go out of the system. In both cases, whether it's going in or out, I don't care. The energy of the system changes. If it's going in, so delta Q is positive, it means that the energy of the system will increase. If it's going out, then delta Q is negative, energy of the system will decrease. So this is first law of thermodynamics, but what it does not tell you is that in some natural processes, we observe that actually delta Q cannot happen both ways, like this arrow here. It always happens in one direction in certain natural processes, and there's nothing to restrict this equation in that sense. This equation does not have any restriction such that in some certain natural processes, delta Q happens in one way. Okay, it just tells you that I do not care whether Q goes in or out. It just changes the total energy level, and that's it. This equation is just concerned about that story. So it does not actually concerned about what could happen really in nature in terms of the direction of the heat transfer. Okay. So of course, people thought about it in 1800s and maybe earlier. And 1800s, Clausius said that we need another variable actually to indicate this direction, and that variable is called entropy. Okay, we need another state variable. What do you mean? What do we mean when we? And that's related to later. Now our topic now, second law of thermodynamics. The first law was energy conservation. Second law is related to this entropy, the parameter called entropy. Now, entropy, we designate it with letter S. It is another state variable like temperature, pressure, and everything. For example, if we have, let's say, a container full of gas, okay, so full of gas, nothing is moving. So if I ask you this question, what is the temperature of the gas in this container? Okay, how would you determine it? I mean, tell me, if I ask you this question, what is the temperature of this gas? Okay, let's say I got this container and then it's a kind of a box, and then I filled it up with some gas, let's say air, okay, N2 plus O2. So I asked you, what is the temperature of this gas inside? How would you determine this? Any ideas? Can you guys hear me, or I'm just talking into a black hole? Any ideas? How would you determine the temperature of this gas?
By measuring it.
Okay, so this is one way of doing it, right? So actually you have two options.
Well, we can calculate the heat transferred from the gas, maybe.
You can measure, so there could be different ways of measuring it. Or you can calculate. The question is, we know how to measure it. That's not a problem. We can insert some kind of thermocouple, or I don't know, some kind of thermometer or whatever. We can actually measure it. But how do you calculate that? Any ideas?
What if we compare two states of the gas in different times with different energies? If we know how much energy we apply to that gas.
So see, you need to know, when I ask this question now, you need to think and you need to come up with things like, oh, I need to compare it to something else, or I need to know the energy level, things like that. The thing is, what is the equation for temperature? I mean, do I have an equation for temperature to calculate? I mean, aside from the global properties, let's say there is no heat transfer, there's nothing, I just filled it up, it's insulated, and right? And then there's no heat transfer, nothing, there's no work. How do I calculate the temperature? So temperature is a state variable. State variable means it is one physical parameter that describes the state of the gas. But when I say state of the gas, what do I mean? State of what? So pressure is another state variable. Similarly, I'm gonna come to that. Entropy is also a state variable. Let me see the chat box. Ideal gas relation. Okay, but ideal gas relation, Onur said we can determine through ideal gas relation. That is correct, but in order to do that, you need to know another state variable, actually a state variable and a physical variable. You need to know the density and you need to know pressure. Okay, how do I know pressure then? So the thing is, I'm not expecting you to know the answer to this question, because this temperature, if you remember, is a global or macro scale variable that is an indicator of all molecular energy, molecular level motions that are related to the energy, molecular energy level of the fluid. So this must be related to something, some equation related to an equation written in molecular level, okay? If you want to really calculate it, because there's no equation in the global scale that you can calculate. Our only option is to measure it, by the way. So, but in statistical thermodynamics, there are equations, okay? There are actually, molecular motion, we do not have exact relations for molecular motion. We have actually probabilistic equations for molecular motion. Probabilistic, like, what do you mean probabilistic? What's the probability of certain molecules hitting each other? I don't know. So that requires a probability density function, right? So those are very much statistical information. So starting from that probabilistic or statistical knowledge of molecular dynamics, I can say, molecular motion, molecular energy levels, I can come up with some statistical equations in molecular sense to calculate the actual global temperature of this gas without the knowledge if there's no heat transfer or nothing. Well, so these are called state variables. Of course, this is out of the context of this class, out of the scope of this class, even out of the scope maybe of the thermodynamics class, because I don't know if they go into this much detail in thermodynamics, but this is the topic of what we call statistical thermodynamics. Anyway, so yes.
Is this the way we calculate the temperatures of molecules in microscopic approach in aerodynamics?
No, aerodynamics, we just, temperature is a given, okay? If somebody tells you temperature is 200 Kelvin here, we say, we assume that this is 200 Kelvin. We do not ask, how did you come up with this? I mean, if this came up as a result of an interaction process with its surroundings, of course, there is some heat transfer involved, there is some work involved. In that case, of course, we do calculate temperature. But if there's nothing involved, what is the temperature of just a stagnant gas molecules? That's out of the scope of this class. Okay. So properties like this are called state variables. They designate, it's like the ID card, you can think of it like that. It's like the identification card of the gas. What is its temperature? So what's this birth, place of birth? What is its, at which year? So you have all these ID information on your ID cards, like, right? So these variables like temperature, pressure, and entropy, these are all called state variables. So they help us to understand what is the state of a current gas. So what is the state of a gas? So what happens is, in an engineering process, now we go one further step. By the way, similarly, we have these, similar to the fact that we have some molecular level equations to calculate temperature, we do have also for entropy as well, okay? But the thing is, in engineering, in aerospace engineering or mechanical engineering, or in flight vehicles that are subjected to compressible flow, those are what we call processes. In thermodynamics, we call them processes. Processes means that this is not the thing that I'm interested in. The thing that I'm interested in is actually this gas goes through a process, whatever process that is. That process could be some heat transfer that is occurring, or the gas expanding, or whatever, and then changes its state. Okay, so initially it's at state 1, and for whatever, so something happens, it changes its state. If all the state variables had initial values like 1 with the 1 subscript or 1 index, now everything is at state 2. Something happened and changed the state of the gas. Okay, and temperature could be higher or lower, pressure could be higher or lower, and entropy can be different. So in engineering processes, we are very much interested in how this happens and what causes this state change of the gas. In aerodynamics, for example, we are very much interested in that. And then after this thing happened, what is the state of the gas after the process happened? That's what also we are interested in, of course, in engineering systems, in also aerodynamics. So therefore, we are more interested in these delta values. So we are interested in delta T, we are interested in delta P's, or the ratios T2 to T1, P2 to P1. And similarly, we are also interested in the entropy change. Okay. So therefore, an entropy change means S2 minus S1, similar to, for example, this is T2 minus T1 and P2 minus P1, or their ratios could be used as well. So the thing is, this is related to, after the basic definition of entropy here, which is a state variable, the thing is, when a system goes through a process, what happens to the entropy of the system? Okay, so that's the question second law is trying to answer, and it says that, well, what is delta S is equal to, or let's say in the infinitesimal sense, let me use that to be more precise mathematically. So if I'm interested in the ds of the system, that could be defined, that is related in thermodynamics to this infinitesimal Q happening at a certain initial temperature of a system, or a reference temperature of a system. If there is certain heat transfer that is happening, this entropy, so this heat transfer changes the molecular structure inside the gas. Molecular structure meaning sometimes it's explained as molecular, let's say, how do they say it? This molecular, it becomes more disorganized in a molecular sense. So it becomes more disorderly, I can say, in the molecular sense. And then that is reflected as the entropy increase. Now, the thing is, this definition, and it's related to a small addition of a small amount of heat, let's say delta Q here. The thing is, so this is how entropy change is related to amount of heat input. But the thing is, this could happen, entropy increase or entropy change, not increase, I should say. Entropy change can happen in two ways, based on how you add this delta Q, okay? In some natural processes, this could be added in a reversible manner. What does this mean? And we defined what we mean by reversibility. It means that you can, I mean, from state 1 to state 2, there could be some heat transfer, but if there is no dissipative phenomena that is occurring, while this gas is changing its state from 1 to 2, and it's gaining some heat from somewhere, so its temperature will increase and everything, but that happens through let's say in a case where there is no dissipative phenomena, there's no friction or nothing. can a process like this occur in nature? It's very rare, okay? Generally, most of the natural processes include some, let's say, dissipative phenomena. But in some very isolated cases, this could happen, or let's say in some very, very much controlled lab conditions, this could be generated. So for example, one example of this is, let's say you have a bowl filled with water, okay, ice cold water, and even there are some ice cubes floating around in the water. And then you get another ice cube, you drop into this water. What could happen is, probabilistically, this new ice cube can get some little amount of heat from this water and actually melt a little bit, or it can cool down a little bit, and it can even get a little bit bigger ice cube. So this amount of, for example, this could be a reversible process, a reversible heat transfer interaction. But of course, this is very much, and in that case, this delta Q corresponds to this, the delta Q that is occurring here. But in reality, and this is how we define formally the amount of entropy change in thermodynamics. But in reality, the entropy change in a real system is actually, if you can measure entropy change, here you said you can measure temperature, for example, okay? You said you can measure temperature. If I ask you, I mean, if we ask the question, okay, for example, can we measure pressure? Pressure is another state variable. Probably you will say yes. If we ask also, okay, can we measure entropy? The answer to this question is also yes, because entropy is a function, this S1 here is a function in reality of T1 and P1, so it can be measured, okay? In reality, S2 minus S1 can be measured precisely if you know temperature and pressure changes. We will come to that. But the thing is, if you measure entropy, you will see that it will be larger than this value, okay? If you have some, if you have some, let's say, reversible heat transfer that is occurring, the actual entropy in a real process where dissipative phenomena is also occurring, like friction-related phenomena, you will see that S2 minus S1 will be larger than this numerical value, okay? So what makes it larger? So let's say ds will be actually equal to this one plus something, plus another, plus some extra amount of entropy that is generated. This extra amount of entropy generated, we call it ds irreversible, is due to all the dissipative phenomena that can happen in a real life system. Friction, mostly friction related, but of course, friction is a mechanical phenomena. In certain chemical phenomena, other mechanisms also exist that create irreversibility. For example, in phase change, for example, if some particles change, some substances change in phases, that also could generate some irreversibility and everything. There are other sources that generate irreversibility. So we say, well, this definition should be modified, meaning that ds, the total real entropy generation for a real system, should be larger than this reversible heat addition amount, okay? And that difference is due to these irreversibilities created due to real life effects like friction, phase change, and everything. So since entropy change can be measured, so therefore it can be quantified. So, and also it imposes a restriction into the direction of this delta Q we discussed, okay? in a natural process, for example, of course, for many centuries, we have been doing observations. One common example is, for example, we have a hot plate, right? This is a hot plate, and on top of it, we put like a cold block of ice. Okay, so this is ice. So as soon as this gets in contact with the hot plate, there will be some heat transfer that is going to start. I mean, you don't need to contact it because of radiative heat transfer. This can also happen, but that's another story. But let's say it's getting in touch, and ice will start to move towards higher temperatures. So it will start to go through, let's say, phase change. It will melt away. This is our daily experience, and the plate will start get colder because it's going there because of the heat transfer that is occurring basically in between these two substances. Let's say it melted away, okay, and then the temperature of this plate went down, okay, and the temperature of the ice actually went up during the process. T ice, let's say T plate, and then it reached to a steady state where now after this process I have my plate, which is a little bit colder, and I have, let's say, a collection of liquid water now on the plate. Now if I ask you, okay, now I want to go back, I want to reverse this process. Well, how should I reverse it? Well, look, I mean, your T plate is now colder. Initially it was hotter. So let's heat up this plate. Let's go back. So increase the temperature of the plate, and let's see if this is actually going to become ice again. Okay. And obviously you might be laughing to this, to the probability of this, because this is impossible, right? This is liquid water, plate is colder, I want to heat it up. This is not going to go back to being an ice. So this is kind of, this process involves complex physical phenomena like phase change and everything. So it is what we call an example of an irreversible process. We cannot reverse it anymore. Once the ice is melted, if I reverse the process of the temperature, let's say dynamics, I want to, heat up the plate again. No, it's not going to make it ice again. So therefore, this this is what we call basically the second law of thermodynamics, imposes this, because this process generates a certain amount of entropy that will be basically S1, S2 minus S1, that will, and here the S is actually greater than 0, it's a positive number, that will be positive. So this is kind of what we have talked about until now, kind of a revision of what you probably learned a lot more detail in the thermodynamics class. The thing is, in terms of aerodynamics class, why is this important for us? Now we will come to that point. So I covered few pages from my notes. I have to go over a little bit. Okay. So in terms of aerodynamics, the question is, first of all, are we dealing with a gas? Yes, we are dealing with a gas, which is air. So does this gas go through state changes when, during its motion at high speed? Well, it might. And if we are especially dealing with high-speed flights, so let's say high-speed airflow around the vehicle, it could go through state changes. Yes, I mean, and we will learn how that state changes happen. And if you remember last week, I have shown you examples, for example, for high-speed flying vehicles, we have these shock waves forming around them. And in reality, what happens is when the air, a flowing air passes through a shock wave, and we will learn how to analyze those shock waves in a short while, the state of the gas changes. So it is both, therefore, so the state of the gas changes means, first of all, its energy level changes. And then second, its entropy level changes. So both first law and second law of thermodynamics now become very much relevant for high-speed aerodynamics. And now the question is, how am I going to calculate? How am I going to relate these two states together? You know, the final state or the second state to the initial state, because if the airflow is changing states, I want to be able to relate them, and most probably, I will know the first state because it will probably is going to be related to my flight conditions, for example, flight altitude, flight Mach number. Those will be my initial conditions, and something will happen to that state, like a shock wave. I will end up with a second state. How do I relate those two? Okay. So, well, if somebody asks that question, you might respond, okay, if the gas is going through a state change, two things can happen. It could go through to the second state through like a idealized process where, for example, there could be zero entropy generation. So this is ideal. Of course, I know that in real life that's not the case, or there will be some entropy generation. Okay, and I know that in real life application process there will be some entropy generation. It will cause some losses and everything. But if I want to compare that real life case to an idealized process where there is no entropy generation, I could basically evaluate how good is my engineering system is working, because in the ideal case there will be no entropy generation. In real life case there will be entropy generation and there are losses. If I did not design that system properly, it means that that system will create a lot of losses, and I can quantify that amount by comparing that real life state to an ideal state where there are no losses. So therefore, the second law of thermodynamics, quantification of entropy generation, quantification of therefore losses or the effect of losses, is extremely important in terms of engineering design. So our starting point, therefore, will be you can think of it as our reference case, where there will be no entropy generation at all. There will be a state change, but no entropy generation. Is it realistic? No. It's kind of a hypothetical process. Hypothetical means, not existing. It's just in our imagination, but it's a reference case, and it's kind of the best case that I can try to get. I can try to achieve. It's like a target for me. So how do I relate these to our aerodynamics? So basically, we start by combining the two laws of thermodynamics together. The first law is basically energy conservation, and the second law is basically related to the change of the state variable entropy, or entropy generation. I can combine these two together. How? Now we will see that. We start that. We will basically do a small we will play with some simple equations to do that. So basically, what we can do from starting from the definition of this, ds is equal to delta q reversible over t. From here, I can actually write this delta q here is actually equal to T, this reference temperature, times ds. Delta Q is equal to T times ds. Now, this delta Q is actually, it appears also in our energy equation. Energy equation was equal to this plus, heat transfer plus work. So this is can be written as equal to T times ds, but what is work? I would like to express, because just in this manner it's not very useful. Okay, I understand it's just delta work, but what is delta work? So generally we relate this to delta work to volume change of a substance. How? I'm sure you might remember from again thermodynamics that we talk a lot about pistons and pistons squishing, gases moving up and down and all that. So basically, if a piston moves down, right, if it just moves down, and then it squishes the gas a little bit, that basically changes the state of the gas. And one thing that happens, it changes the volume of the gas. So the volume of the gas will change. And if if you move the piston down, you will, it could basically, it is related to the work done by the piston, because you have to do it with a certain amount of force and you move the piston. So F times X basically is related to the work. And generally in thermodynamics, we relate amount of work to the volume change happening at constant pressure, for example, and times dV. So we invoke this into the energy equation, and then we end up with this equation. Now dE becomes equal to, actually this should be minus P times delta V. So T times ds minus P times delta volume change must be equal to the energy change. And from here, now I can write T times ds is equal to the energy change plus P times the volume change. Okay, so now this equation is a little bit more useful, because now I have entropy in it. First of all, I combined both first law and second law together into a single equation. This equation represents energy conservation, and this equation also represents entropy generation. So one thing, let me just double check from my notes. I don't want to make a mistake in these equations. One thing that I would like to relate this to is also to another important parameter that we use frequently in thermodynamics, is basically what we call enthalpy. We use the small case letter H generally for enthalpy, and enthalpy is related to, its definition is, it's a combination of internal energy plus the amount of, or it's related to the motion or pressure and volume changes that are happening in a fluid. So this is enthalpy definition. Well, if I take the dH of this, so if I take the infinitesimal amount or the derivative of this, this must be equal to dE plus now d of P times volume, and dE plus d times P times volume will be, of course, equal to P times dV plus V times dP, right? V times dP. So, well, this is exactly the same as this term, as you can see here. So, which means that the combination of the first law and second law thermodynamics equation can also be expressed in terms of enthalpy. So let me now write that equation. So from here, from here, I can write now TDS. Therefore, TDS will be equal to basically dH minus VdP from this equation. So, I can write, also I can go one further step. I can write dH, this is equal to dH minus, I know specific volume is equal to 1 over density. We talked about it. So basically I can directly write dP over rho. Okay. Good. So this is one important equation. So TdS is equal to dH minus VdP or minus dP over rho. This is important. The question is, what is dH? Okay, enthalpy. Okay, this is fine, and this is its definition. But how is this related to temperature? Because I see temperature on the left-hand side, I see pressure and density on the right-hand side, but I do not see any temperature. But in fact, I do know that both enthalpy and in fact, internal energy as well, the E, are related to temperature, and we actually have already seen it, if I remember correctly, last week. We know that dH is actually related to temperature through the specific heat at constant pressure, dT. And similarly, internal energy also is related through another, well, I'm not going to say constant, but a parameter, because we know we have discussed this before. Cp and Cv are also, can be also, let's say, constants of functions of temperature. So Cv times dt, I do know that. So basically I can replace the H in that equation to reflect that. So I can write basically TdS now becomes equal to what? Cp times dt minus what? dP over rho. Do I want to write that now? Okay, I will. Okay, I will currently keep VdP to be consistent with my notes. Okay, that's good. So what do I use it for? What do I do with this equation? Well, I take this T on the left-hand side, I take it to the right-hand side because I want to obtain an expression for entropy generation. So this becomes equal to Cp times dt over T minus basically specific volume over T times dP. Now, what is this? We know that from equation of state for an ideal gas, which we discussed also last week, I know that P times V is actually equal to R times T. So, ideal gas equation of state. Okay, so therefore V over T is actually equal to R over P from this equation. So I insert this into the ds. ds will be equal to Cp times now dt over T minus R, or maybe let me write it this way. Let me delete it. It's going to be equal to minus R times basically dP over P. Okay, so now I can relate two processes to, I mean, the two states of the gas together. A gas that is going through a process. And in terms of our class, aerodynamics 2, a high-speed aerodynamics at this stage, this is related to the change of the state of the gas due to, as it's moving around a high-speed vehicle. And the gas can go through a lot of physical processes, its state will change, And if I would like to ask the question, state will change, meaning its temperature will change, its density will change, its pressure will change. And to answer the question, well, how is its entropy is going to change? I need this. I can make use of this equation. This equation tells me if you know the temperature change dt, and if you know the pressure change dp, you can calculate the entropy change for that gas, air in our case, going through state changes as it moves at high speed around a certain vehicle, certain missile, certain, I don't know, fighter aircraft or whatever. Okay. Of course, so the question, and then, I mean, starting from this point, basically, in order to calculate the total amount, this is for an infinitesimal change in entropy, ds, right? If I would like to calculate the integral amount, the total amount of entropy change, this right-hand side needs to be integrated, obviously. So this is S2 minus S1. So that must be basically integrated from the first state to the second state, Cp dt over t, minus integrated again from the first state, now P1 to P2, now R times dP over P, so that I can get the global change in the entropy as the gas goes through this process. We defined, let me talk about this, then we will have our break. We defined last week what we call, I mean, we first defined what we called a perfect gas, if you remember. And also we defined what we call calorically perfect gas. If you remember, we defined calorically perfect gas. This is kind of an idealization of a perfect gas such that Cp, these values, Cp and Cv are constant values. And if you remember, the gas constant is equal to Cp minus Cv. We discussed this also last week. So therefore, R is also a constant for a calorically perfect gas. Why am I telling you this? Because if those are constants, I can take these constants out of the integral. Cp and R can be taken out of the integral, so that now for a calorically perfect gas, S2 minus S1 can be written basically after the integration. After the integration, meaning I need to integrate T1 to T2 dt over T. That integral is quite easy. It's going to be equal to ln T, or ln T2 minus ln T1. So ln basically T2 over T1. So it's going to be equal to basically Cp times ln after the integration T2 over T1. And what else? Minus R, so ln P2 over P1. Okay, so that's if I know the macro scale temperature property and pressure state properties of a gas, I know if I know T2, if I know T1. Well, how do I know T2? That's, we will learn how to calculate T2 later for different physical processes that's occurring around a high-speed vehicle. We will learn how to do that later, but let's say we know T2, we know T1. If you know P2 and P1, and if it's a calorically perfect gas, I know the values for Cp and R, which means that I can actually calculate the entropy rise, because entropy is supposed to increase, entropy change or entropy rise, entropy increase that is occurring through that physical process. We will give a break now, but starting from this point now we will talk about, so this is for a real process, by the way, because there will be entropy generation. Now we will talk about what if it's not a real process? What if it's an hypothetical ideal process where there is no entropy generation. So the left-hand side of this equation will be 0. So we will see that after a short break. It's 2:32. I'll meet you again in 8 minutes. Okay, everyone? So let's meet again in 8 minutes. Okay, so sorry, I need to start. I need to do some stuff. So I'm starting a little late. 240, what is 245? So continuing our discussion on this entropy calculation, one thing that is important in terms of any analysis of any compressible flow in general, and in terms of our class, we are dealing with implicit compressible flows, is to be able to calculate this entropy generation. But of course, first we would like to understand the ideal case where there is no entropy generation, as I was saying. So what if this S2 minus S1 is actually 0? So delta S is actually 0. If you remember, we defined this as an isentropic process last week. Isoentropy, so the same, which means the same entropy. So entropy is actually not changing. We call it isentropic process. And just to remind you again from last week, an isentropic process is basically adiabatic and a reversible process. This is how it's defined. So it's an adiabatic process which means that delta Q is actually 0. There is no heat addition. Okay, it's a reversible process, which means that all the irreversibility related entropy generation due to friction or whatever is ignored. Okay, so this is also 0. So S2 minus S1 basically is 0, so that makes the left-hand side of this equation 0. So I can write from here, now 0 is equal to, well, let me go one further step. So basically it makes Cp times ln T2 over T1 is equal to now R times ln P2 over P1. So this is now my equation for an isentropic process. So of course, I can make use of this equation because I can now write a relation between the pressures and temperatures of the two states of the gas. P2 over P1 now becomes equal to T2 over T1 to the power, and because it's a natural logarithmic equation, Cp or power equation equal to Cp over R. Okay. We can do just a little exercise in terms of what is Cp over R, because I know Cp minus Cv is equal to R, and I also know from last week's classes, we defined Cp over Cv is equal to gamma, specific heat ratio, right, gamma. So from these two equations, I can actually obtain a value for Cp over R. How? Because I can, from the first equation, I can write this is Cp minus, instead of Cv, I can write Cp over gamma is equal to R. So from here, basically Cp 1 minus 1 over gamma is equal to R. So from here, Cp over R is actually equal to basically just do the arithmetic and you get gamma over gamma minus 1. Okay, so I insert this into the pressure temperature relation. Now I get my isentropic relation P2 over P1 is equal to T2 over T1 to the power gamma over gamma minus 1. Just as a side reminder from last week, the gamma value for air, assuming it's a calorically perfect gas, so Cp and Cv are constant, and we have seen those constant values last week, if you remember. This is equal to 1.4 for air, if you remember. So now, for an isentropic process, I do have a relation that is basically relating the two states, two states of the gas and two state variables of the gas, right? If as a result of a process, as a result of an isentropic process. Now, as a result of that isentropic process, if pressure changed, it could increase or decrease. We could immediately calculate how much temperature will change as a result of the same isentropic process. All we need to do is to calculate this exponent and calculate this equation. We know that if I go back a few steps to our original relation, this dP over P. If in the original relation, if you remember, we originally had a specific volume. So this means that this equation actually can be written not only in terms of pressure changes. I mean, this equation here that I'm talking about, this equation can also be written not only in terms of pressure changes, but also it can be written in terms of specific volume changes, which means density changes. That version, first let me write that down. That version for S2 minus S1, same entropy change can also be calculated using CV ln T2 over T1 and plus R times ln V2 over V1. Okay, it can be also written in terms of specific volume changes, and specific volume we know that is equal to 1 over rho, so which means that we are talking about now density changes. So starting from this equation, a similar relation can be obtained between now rho2 over rho1 ratio related to T2 over T1 ratio. But the exponent obviously will be slightly different. This is going to be equal to 1 over gamma minus 1 when you make the proper derivation similar to the one we did for pressure temperature relation. We now have a density temperature relation, the density of the gas in between those two states. So therefore we can combine these two relations. In fact, this one here and this one here, I can combine to write like this. P2 over P1 is equal to rho2 over rho1 to the power gamma, and T2 over T1 to the power gamma over gamma minus 1. Okay, these are called isentropic relations for a gas that is going through an isentropic process. And as I was telling you, it's important for us to know this, because we know that it is not real, and it cannot happen in real life, but it is the best that can happen in real life, or let's say it's the best case that we put on in front of ourselves as a target when we design an engineering system, and that engineering system will experience, will enforce, let's say, some changes to the airflow around it. So the state of the gas, state of the air will change. Then if that airflow state change generates some losses in real life, I would like to know what would happen if there were no losses. So my engineering system basically will be the best ever that can be designed with no losses, how much would the change that could impose on the gas that it is operating inside, like the air, for example. So it's a very basic and very good reference for me to compare my real engineering processes. So these relations will be very much useful in this class. We will see that very soon. Now we talked about basically the starting point of all of our discussion was we talked about thermodynamics, right? We talked about first law of thermodynamics, second law of thermodynamics, the definition of the state variable entropy, and then we combined these two laws, I can say, first law and second law, and then we obtained this relation between entropy generation and related to temperature and pressure variations and density variations, and we said, what if it's isentropic? We ended up at this stage. Now, we need, especially related to high-speed aerodynamics, we need to formally introduce another concept. We have been talking about the fact that the first part of this class in this course is related to what we call compressible aerodynamics, or inviscid compressible flow, to put it more in a more precise, to define it in a more precise manner. Compressible inviscid flow around bodies. Now the thing is, and we say that, okay, look, last semester in aerodynamics 341, we actually dealt with incompressible aerodynamics. So we keep using this word a lot, incompressible, compressible. Well, then the question is, let's remember also what is this thing called compressibility, right? Well, we teach you that concept in the first few weeks of the fluid mechanics classes. I mean, in fact, this semester I am teaching one section in fluid mechanics, and I just talked about definition of compressibility just yesterday. Yeah, it's the second week of classes. So you probably learned it before. So let's also, it's time for us to formally remember to write the equation and define what is compressibility, because we keep talking about it a lot now. Now it's time, because we are dealing with high-speed flying vehicles, and we are talking about the fact that the flow, airflow around high-speed flying vehicles are or is compressible. So what is compressibility? So let's remember that as well. It's a good point to remember that now. So definition of compressibility. Definition of compressibility. So generally, when we are talking about this, there's an equation. By the way, compressibility is a physical property of a substance, like viscosity, for example. When we talk about, okay, this fluid is, you know, it has a viscosity of this and that, there are some numerical values, so this fluid is more viscous compared to this other fluid. Like honey is more viscous compared to water, or water is more viscous compared to air. Similar to that, compressibility is also a physical variable. Like we talk about compressibility of water, compressibility of air, compressibility of honey, compressibility of silicon oil, or whatever. Different fluids have different compressibility levels. A compressibility, when we are describing it conceptually, let's say we have a certain amount of fluid, it has a certain amount of volume. So when this is subject to some external forcing, let's say some pressure field around it, okay? Some pressure field around it. So let's say in this manner, it's under steady state condition, meaning that it does this fluid volume it does have a constant volume V, and it is subjected to a certain pressure field around it, P. So it's at steady state, meaning that it is holding its shape, right? It's not deforming. It's nothing is happening to it. There are no changes in volume. There are no changes in pressure. Everything is steady state. But somehow, one morning I wake up. I said, "What the heck? Let's increase the pressure." Okay, let's increase the pressure to P plus dP. And the fluid, and since this is not a solid, the fluid will say, "Whoa, wait a second. Why did you decide increasing the pressure? I cannot resist to that. So I have to go through a volume change, which is V plus dV." Okay. And so basically, which means that, well, now this shows that there must be a relation between pressure change and volume change for a fluid. Okay, when I change pressure, and for, let's say, I have a certain type of fluid, it could be water, for example. When I change pressure, there will be the water will go through a certain volume change. But let's consider an alternate case. Let's say it was not water, but let's say it was air. If I increase the pressure the same amount, same dP, will the air go through the same volume change like the water did? Okay. The answer to this question is it's probably no, because I mean, just from our gut feeling or from our engineering, let's say, senses, we can say probably air will go through a larger volume change, because it's air. Everything, its properties are different. See, I'm having difficulty in answering this question. So the answering this question, it will be more easier if I actually quantify this. I define a variable called compressibility of that substance, and it actually relates these two cases. So I said, generally we use the Greek letter tau. We say this is equal to definition of compressibility of a volume of a substance is 1 minus 1 over volume, and then dV over dP. Okay. We do have a minus sign here because it's to reflect the fact that as we go through a positive pressure change, dP, in that case, if dP is positive, I try to sketch it here, increasing in pressure, so dP is positive, will result in a decrease in volume. So dV will be negative. So when this is positive, this will be negative. And with this negative sign, tau will be positive, because as I told you, this is the physical property of a substance that cannot be a negative number, right? So the right-hand side should result in a positive value. So it is consistent with the physics or the conceptual physics that I just described. So its definition is minus 1 over V and times dV over dP. So incremental volume change that is happening to an incremental change in pressure. So some fluids have high levels of compressibility, some fluids have low levels of compressibility. And generally, if you might remember again from fluid mechanics classes, liquids in general, so liquids are fluids, liquids generally have low levels of compressibility, meaning that if you change delta P, liquid volume change will be very, very small. There will be a volume change, but it will be extremely small. So, I mean, sometimes it's even so small that we approximate them as what we call incompressible substance. Solids are mostly, I mean, metals, for example, extremely incompressible, so their compressibility levels are very, very low. Liquids are very close to being incompressible, so their compressibility levels are also low, but not gases. Gases, it's a totally different story. The compressibility level of gases, any gas for that matter, is quite high compared to liquids or solids, I must say. So any slight change in dP, increase in pressure, will cause a good change, a good amount of change in volume. It will get compressed, or if it's a positive dP, it will get compressed, volume will get reduced. Or opposite can happen, obviously, if you reduce the delta P, if you reduce the pressure, I mean, so the gas will instantaneously expand, almost instantaneously expand and occupy a larger volume. So gases respond very quickly, and air is one of those gases. So therefore, compressibility level of gases is very, compressibility value of these gases, I must say, is very, very high. So the thing is, if sometimes, when you are compressing or trying to increase pressure or decrease pressure, so this is of course a thermodynamic process as usual. If this happens at constant temperature, we call it let me see, we call it, this could happen isentropically or isothermally. The first one, we say the value of tau, we call it isothermal compressibility of a substance. So we define it as tau capital T. It's basically minus 1 over V. Now, the V over dP happening at constant temperature. This is one form of compressibility. There is also what we know as isentropic compressibility. Isentropic compressibility, which means that tau happens, or this pressure change, compression, decompression, or whatever, happens through an isentropic process. And as I said, this is a increasing pressure, decreasing pressure. This is basically a thermodynamic process. If this happens isentropically, that's called isentropic compressibility value. So now S is actually a constant, not temperature. So both these tau T and tau S basically are very precise thermodynamic variables of the fluid. So these are thermodynamic variables of the fluid. Okay. Now the thing is, this compressibility is quite important for us, because we say we are dealing with compressible flow, which means that airflow, for example, the flow around a fighter aircraft, if it's fast enough, air actually is a gas, so it is compressible, meaning that it will go through these specific volume changes, which means that it will experience density changes, okay? So density is not a constant. For the density of the air will change. Now, the thing is, experimentation over the years in terms of how air behaves when flowing or when moving at different speeds, people have seen that depending on how fast air actually moves compared to the speed of sound, local speed of sound, it can behave, in some cases, its compressibility level actually, it changes. And sometimes it can be very much compressible, and sometimes it can have even very low levels of compressibility. Now, the thing is, how do we know that and how can we actually quantify that? The best way in aerodynamic studies especially to quantify this is through this parameter called Mach number. Okay. If you remember, we talked about Mach number in terms of, for example, categorizing flight vehicles, right? High-speed vehicles, I mean, supersonic vehicles, hypersonic vehicles, subsonic vehicles, high subsonic vehicles, transonic vehicles, and vehicle means all the flying systems that we design, whether civilian or military, whatever. Mach number is a good way of actually characterizing the level of compressibility. Okay, so its definition, if you remember, is basically the velocity of the flow, airflow, to the speed of sound. And in aerodynamics, generally we use the letter A for designating speed of sound. In general fluid mechanics, sometimes the letter C is used to keep it general, because fluid mechanics is general, more general than aerodynamics. Aerodynamics is a special topic of fluid mechanics. So, but in aerodynamics, we use the letter, small case letter A to designate speed of sound. Now, Mach number, the last name of the Austrian scientist or physicist Ernst Mach, is the ratio of your airflow speed, and this is of course very much related to your flight speed of your vehicle, to the speed of sound of the gas. Now, this is an indicator of generally compressibility, and let me write this down first. This is speed of sound. This is a level of indicating level of compressibility, and it can be both shown from theory and from experiments. We know that if this Mach number, I mean, for the cases, airflows that are moving at Mach numbers less than 0.3, the compressibility level of air actually is very low. And in reality, so density does change. It doesn't mean it's in reality it does not change, but the changes in density are so small that we assume the flow almost, I mean the airflow, let's say, almost behaves like an incompressible gas, incompressible substance, I can say, incompressible. If for all the other cases, for all the cases that are larger than 0.3, air experiences, I can say, airflow experiences quite significant density changes or specific volume changes when it's subjected to pressure changes. So you can say, well, why does the air experience pressure change? Well, the answer to this question is, well, you are an aerospace engineer, you design aircraft flies, and around, for example, on the top of the wing, you manipulate pressure. Sometimes, I mean, at the top of the wing, you force it to be less, to become less than the bottom of the wing by designing certain geometry. So you manipulate the pressure. You manipulate pressure means you are, messing up with the pressure field. And when you mess up with the pressure field, sometimes you increase pressure, sometimes you decrease pressure. Then, of course, it goes back to this case. It goes back to this case. When you start messing up with the pressure field, the question is, will the fluid particles react to that? Okay. Well, if the fluid particles are moving fast enough, meaning faster than Mach 0.3, they will react to that. They will react to that, to those pressure changes that you are forcing on the airflow because of your geometry of your fighter aircraft wings. Then density of the gas will change. So Mach greater than 0.3, these changes are quite significant. Incompressible meaning density can be assumed to be almost constant. and compressible meaning it's not constant at all, and we need to calculate it. Density changes needs to be calculated by equations. Okay? Good. So therefore, when we talk about compressible flow, this is extremely important for us because especially in the context of this class, as I was telling you last week, we at this first part of this class until week 8 or 9, we will be dealing with high-speed flying vehicles. High-speed flying vehicles meaning any vehicle that flies faster than Mach 0.3. So high subsonic, supersonic, hypersonic, and also transonic between 0.8 and 1.2. Of course, the flow physics becomes a little bit different. So, but in any case, anything that is going to be flying faster than Mach 0.3, this is our case now, and we know we are dealing with compressible flow. Flow will not be a constant. Any pressure change in the flow will generate a density change. And as engineers that are trying to design flying vehicles at those speeds, we need to be able to calculate, first of all, know the theory, the equations behind those, and therefore using those theories and equations, we need to be able to calculate the changes happening to the airflow. Why am I interested in calculating the changes happening in airflow? Because I want to be able to calculate the aerodynamic loads on my aircraft. Okay, that's the final and ultimate purpose. Okay, so after these, let's say, revision of concepts of fluid mechanics, thermodynamics, and compressibility and everything, now the question is, so what are those equations? Okay, what are those equations that I can use as an engineer to calculate the actual forces on an aircraft that is being subjected to those compressible airflow conditions? So our subject is now governing equations.
Hocam,
Evet.
why is the barrier for us Mach 0.3 and not something else? What is special about it?
It's basically the thing is from experience, and experience meaning from measurements done in this field, up to Mach 0.3, measurements of what? For example, measurements in density. If you measure density of airflow flowing at different speeds, you would see that I mean, you could produce, as a result of those measurements, for example, you could produce variation of airflow density with Mach number, for example. You will see that this actually, or you know, in a wind tunnel test, for example, around an airfoil or something, you can measure density, you can change Mach number, and you will see that, I mean, people have seen through experimentation mostly that less than Mach 0.3, density does not change much. And if it's faster than Mach 0.3, you start to observe significant changes in density, okay?
Okay.
It's based on mostly measurements, but there's also, we will see later, that there's a theoretical basis as well. Now, governing equations for inviscid compressible flows. Of course, first of all, there's no such thing as governing equations for inviscid compressible flows. We have one set of equations in reality, which are the governing equations of fluid motion in general, or governing equations for fluid motion, I can say, which is basically conservation of momentum, conservation of energy, and all that. So conservation of momentum is Newton's law of motion. conservation of energy, just as we have seen today and last week, conservation of energy is first law of thermodynamics and all that. So there's only one set of equations. But what I'm trying to say here is that when I say governing equations for inviscid compressible flows, the original equations, governing equations, actually get modified, in a certain sense that are valid when the flow is inviscid. So we ignore the effects of viscosity. And now they are compressible, meaning that density changes are significant, okay? So normally, the first thing that we might discuss is that if the flow is incompressible, okay, flow is incompressible, the main, for an incompressible flow, the main changes that are happening in the flow, or the main unknowns in our flow to determine the state of our airflow, is basically pressure and the velocity of the flow. So P and V. So those are what we call the primary dependent variables for an incompressible flow. Let me write this down. For an incompressible flow, and when I say incompressible flow, it could be airflow for Mach less than 0.3, or it could be water flow, right? Water is quite an incompressible substance. So for an incompressible flow, primary dependent variables are basically pressure and velocity vector. So it has three components in three directions. So basically we need, in order to solve this, one equation, basically two equations. I mean, one equation, we have two unknowns, considering vector as one single unknown. In reality, this is three unknowns. This is one unknown. So in reality, we have four unknowns. We need four equations, and these are actually one continuity equation, and basically a momentum equation for each component of the velocity vector. So, or each component of the momentum, I can say. So three conservation equations of momentum. Okay. And if you would like to express or calculate temperature, you can relate, because density is not changing a lot, right? Density is not changing a lot. So if you would like to calculate temperature, you just can use equation of state, but it's just a multiplication, or let me try to show it like that. Equation of state is P equals rho RT, right? So from the momentum equation, you have pressure. Well, this is not changing much for incompressible. This is probably more or less a constant. R is a constant. So temperature is just a constant times pressure, basically. Okay. So you do not need to solve an additional, let's say, conservation equation. That's not the case for compressible flows. Okay. For compressible flows, now, then we know now that density is not a constant anymore, okay? So I don't know what density is. I mean, I cannot just say pressure will be equal to, or temperature will be equal to pressure divided by a constant, because I don't know what density is. So which means that I have one additional unknown now. I have P as an unknown. I have three velocity components as an unknown. And also I have now rho as an unknown. And of course, temperature is always, of course, needed. Temperature is an unknown. So here, maybe just to be exact, here I had one pressure, three velocity, and of course, one temperature as an unknown. So I had five unknowns, but I had here one continuity, 3 conservation, and 1 equation of state. So I have a closed system. I have 4 equations for unknowns, but now I have a fifth unknown, which is density. So so basically I need an additional equation. That's what it means. I cannot live with these 4 equations, and that additional equation obviously will be conservation of energy equation. So that makes now 5 unknowns. So now I need 5 equations to have a closed system to be able to, for me to solve. Now that additional equation, so 1 continuity, let's write them down again. 3 momentum conservation, 1 equation of state, and I have now 1 conservation of energy equation. So that makes it now a closed form. So therefore, if we would like to deal with now compressible flow problems, we need to, and especially in the special case of inviscid compressible flow problems, we need to write our equation set now. That is going to be valid for inviscid. So if I see any viscous terms in my conservation equations, I have to ignore them because we are dealing with inviscid flow. But I need to keep proper terms so that that will allow me, the equations will allow me such that variations in density or possible variations in density, that physics will be reflected in the equations. So let me write, of course, the simplest of all, or simplest, but probably the most important of our equations, the continuity equation. The next we will continue tomorrow. Continuity equation. Continuity meaning, just to remind you again, mass conservation, right? Conservation, the mass of what? Okay, mass of what? Mass of a fluid particle. So if this is your fluid particle moving in a medium, so we say that while this fluid particle is moving, it is interacting with its surroundings. It can be subjected to different forcings around it. So sometime later, its shape could be totally different. It could look like that. But what is not changing is the mass inside. Its mass inside is not changing. Conservation of mass or continuity equation says that mass of this is not changing with time. Okay. So we know that. So how do we calculate mass? Is rho times volume, right? That's how we calculate mass. But of course, this equation is written in the sense of following this fluid particle around. We call it Lagrangian approach. That's generally something we do not prefer to do in fluid mechanics, if you remember, because otherwise you would be in a really bad situation. You would have to follow every single fluid particle that you can imagine in the domain. You don't want to do that. Instead, we embrace what we call Eulerian approach. And in order to go from this equation, which is written in Lagrangian sense, to Eulerian approach, in which we are not following fluid particles, but we fix our position in space, we define a control volume, and you basically watch what's going in and what's going out. So that's called control volume approach, to refresh your fluid mechanics memories. So the relation or the bridge between this Lagrangian approach and the Eulerian approach is called Reynolds transport theorem. And Reynolds transport theorem basically gets this equation and converts it to a Eulerian approach, which looks something like this. So we have this three integrals with a closed loop, which means you have selected a control volume in space. So rho times the volume. So this is mass, basically unsteady term of mass generation or destruction inside that volume. and double integral, again closed loop. So this is a volume integral, this is a surface integral of mass coming in and out of the surfaces that is surrounding this volume. That must be equal to 0. So what I'm basically trying to say is, if you have a control volume here, some mass can be going in from all over the place. Some mass could be going out from some faces. And I don't know, with some magic, some extra mass could be generated inside. Whatever is generating it, some chemical reaction or whatever, some nuclear reaction or whatever, some extra mass is being generated. But in the end, generated mass inside, coming in, going out, that must balance together. And that should end up to be 0. Mass coming in must be equal to mass going out. We call it the integral mass conservation equation, integral equation of continuity or mass conservation, or through Stokes' theorem, and we can actually represent this in the differential sense. You can write a differential equation for this, d rho dt plus the Nabla operator gradient dot product rho v must be equal to 0. That's the same equation again. So this is the differential equation of continuity, or continuity equation in differential form, you can say. So yeah, that's the first law that is important for us. Let me make my final comment, and we will finish up today's lecture, is that as you can see, this equation does not assume rho as a constant. Rho is not a constant. Okay, it's a variable, and that variable has to satisfy this derivative, the rho dt. It means rho can be changing in time, and also this term, it means rho also can be changing in space. So if you have a certain domain, anywhere in this domain, rho can be different, and it can be also, if you look at this domain, let's say it's the domain at t equal to 0. Let's say you look at it at a t equal to time, or t equal to t0, you take a look at it at t0 plus delta t, you might see a totally different rho field, density field. So this equation reflects this physics, okay? So it's a compressible form of continuity equation, you might want to say. I think we have seen the incompressible form last semester. For incompressible flow, we know that now rho is basically more or less a constant. Of course, if rho is a constant in this equation, there will be no d rho dt term equal to 0. And in the second term, you take rho out, and then you end up with a simple equation for continuity for incompressible flow. Okay, everyone, so I would like to stop here, and we will continue with the other conservation equations, momentum and energy, tomorrow afternoon, okay? So do you guys have any questions? Okay, no questions, then I will meet you again tomorrow at 1:40. So let me stop recording.